Somebody asked me last night, just at the end, if I was going to talk about love. And I said, I'm bound to talk about love. And Andy, one of you, was married this Christmas time in California, and I went to his wedding, and he asked me to recite a poem that I wrote at his wedding. And I did so, and I really felt very moved to be invited to have my thoughts incorporated in somebody's wedding. But I also was very interested. The people who were at the wedding were many older people as well as young, and they came up and told me they liked it. There were many faces. I looked around at those at the wedding, and I didn't know, my wife and I didn't know them, and so I wondered whether they would care for that kind of a poem. But apparently I was really very deceptive, because older men that I would not have thought had been really particularly interested in it came up and said they liked it. Last May 28th, I was sitting working in our apartment on the 31st floor of the Society Hill Towers here in Philadelphia. And the windows were open. It was a lovely, really beautiful late spring feeling, just on the edge of June. And I was actually writing about the twilight of the power structures, which is economics, and to my astonishment, really, this never happened to be quite that way. I suddenly had a poem, and I had to write it out, and the poem goes as follows: Why yours truly? I'm not yours. You're not mine. My years of life is 79. Mysteries deepen. I opine. Curvaceous, silcaceous, sylphaceous you. I'm nigh inefficacious. What may we do? I can't eat you and have you too. Let's enjoy laughter and wisdom too. You're eternally lovely, the truly you. You can't see me, I can't see you, but we may know one another, and sometimes do. Then learn that we both love only all that's true. Wherefore we both love the truly you. I love you forever, the truly you. And I really feel this very, very deeply about my feelings about humanity. I really do love humanity. It can be very obstreperous. Achievement can be very obstreperous. Humans can be very misbehaved, but I really do tend to a really very deep sense of affection. I get particularly in love with those who are participating in experiences which we're going through together. I got to tell you how much your beings mean to me as I sit here, and I'm very deeply aware of your eyes. I can see them all night. And I'm so absolutely overwhelmed by the mystery of the experience that we all go through, of life itself. And I'm so astonished at myself and how the way other people also take everything so for granted, that this is the way it was meant to be, and so forth. And there's a big picture, but all of this is the more I think about it, the more difficult it is to understand how such extraordinary awareness can occur as that of life. And you certainly are feeling with me our times and the critical condition I'm confident all of humanity are going through this very, what I feel is to be a great test. And the thing that I have written and call here complexion in 1975, I'd like you to look in the Webster's dictionary at the meanings for complexion. And this is the most highly concentrated kind of statement I could make. And I'm quite confident it is a very heart essence of things, all the things I'm saying to you. And it is big and tight, and I've been rewritten time and time and time again. I've studied every word I use and looked at, changed them all around and keep sorting it out. Janet's here, and she's retyped it. I don't know how many times these things go on and on and on. But please remember, it is highly concentrated, and that I don't do it to have it flow fast. So I hope that I'm so accurate that it will be lucid and could flow. But there's a whole lot of thought packed in, so it needs to be digested. I do recommend reading it through quite fast, but then coming back and taking it easy. I'm going to, with the hours that are left to us now, go on some more with the design science and experiences in the design science, and thinking about then, I want you to think about the integration of many things I've given you, outset grand strategy, how not to miss anything, how not to miss any of the parameters at the very outset. Discovering that the thinking had geometry, and going into the geometries, and discovering principles of intertransforming, and discovering which geometries give us the greatest strength, doing the most with the least. And as we go in to the structures I'm going to go through tonight, I think you'll feel very powerfully the geometry. These are all, remember, I could get to the point where we noted that we had conceptuality independent of size or time, and then we introduced the phenomenon of time, and introduces frequencies of modular subdivision. And we saw how that was patterned in relation to the vector equilibrium as either radius or chord, that the time increments, the frequency increments were in the exact synchronization of both the radial, which would be radius, and the circumferential, which would be the containment or the gravity. Really it is a united field theory of the gravitation and the radiation, but finding that the gravitation was more favorably arranged, the same 6 vectors, because they came back to themselves, and they used the mass intertractability to have a containment, whereas the explosives, the radiants, were trying to come apart and were not helping one another. The further apart from one another, the less they could help one another. And they did not operate together, they operated independently. So really the difference between synergy, or the behavior of wholes, and the behavior of the parts considered separately, we see the parts coming apart, but not being as effective anywhere nearly as when you can actually come back to yourself and really know the word understanding. I find the word understanding when I do the thinking. I want to understand. When I finally find out where are those star points that are dividing the universe in the inside and outside us, so that finding that there are 4 stars, but there are 6 relationships. And the understanding is finding what those relationships are. When you have all the relationships of your system, then you understand. Now, I hope you'll I'm doing so much talking and you listen to me so intently that I don't really give you the opportunity to, at this time, to begin to develop grand strategy and try to integrate all the things I'm saying. But I've deliberately tried to present the things to you coming from the whole to particular in a way that we continually have to realize that this is related to what I've heard before. And I'm very eager that you feel the absolute interconnectedness of everything. And so I'm now thinking a little about all the lessons I had of the little individual trying to do his own thinking, taking the initiative in the face of the great organized power of society and the great power vested in great states and corporations and nations, and seeing what the little individual could do. And there is that document, this 4D that I spoke to you about. As I wrote 4D in really great passion back in 1927, at the time that I had made my resolve to peel off and really do the 90 degree, pay no attention to earning a living anymore, I look back then and I see it was terribly overloaded with negative criticisms of things that do go on, and I've learned not to dwell on the negatives and really try to. I assume any negative I experience is a gift. This would make me really look and see what is going on, try to understand what nature is trying to do, not to emphasize the ignorance of little humans who are born ignorant in relation to what is happening to them. I gave you the circumstances of the Beach Aircraft House last night, and gave you my resolve after that experience to commit myself now to shells, because I saw that a great many were inherently preoccupied in a direction where some success would really develop in what I call the autonomous package of the equipment you need to keep yourself clean and so forth, and to take care of your processes. I showed you the picture of the bathroom, but I did not have the picture. I thought I had it there, but I recall now that we didn't look at it. Following those bathroom pictures, I came to doing experimental work with an idea that I had had in 1927, the time of the Dymaxion House, and what I undertook to do real experimental work with occurred in 1948 at the Institute of Design in Chicago, and 1950 at Yale University Architectural School, two separate operations, where we discovered that instead of having to have a wet bathroom where you fill the tub full of the water and have showers and so forth, that there's something to be really learned about cleansing of the skin, because I had the experience in Navy back in 1917 of being in the engine room and getting very oily and greasy and coming on deck, and a very short while later, without anything to actually clean myself up, finding my hands very, very clean and my face clean, and it was this when there was great wind and there was fog, and somehow this wind and fog had a cleansing effect. I was amazed by it, without any soap or anything to help it. So I got getting into what I call the fog gun experiments, and I'll point out, too, coming back to our experience with hydraulics, we've been thinking about hydraulics and pneumatics. The hydraulics are non-compressible, very much more dense than are the gases. Therefore, when we get to trying to be economical with water and cleaning, if we get into a needlepoint shower, you get where the kinetics of you get high pressure, but very fine little droplets, and then because it is non-compressible, it really is a little bullet, and you get to a point where the needlepoint shower will break your skin, and that's as far as you can go. And still you're not getting very much economy with your water. What I found you could do would be to take compressed air and atomizing water in the compressed air, that the air itself then very much less a weight than the water, then the air being also pneumatic and so forth, it could really penetrate your pores under great pressure without hurting you at all. You could have really very powerful pressure of air on your skin, and it doesn't hurt at all. And I found that it could get into the pores, being really finer molecules than the water molecules. So if you get into the pores and try to atomize some water and went in with it, there could be a scavenging out of the pores and bring just really float the dirt away. So we went in for such experiments, and you've seen human beings cleaning buildings, great operation going, and it looks like they're using steam up there. It isn't. It's very high compressed air with water atomized in it. And it's cleaning that building just beautifully, doing just what I said. And if you take one of their kind of guns, you might think it would really hurt your hand. It doesn't hurt you. It might make your arm go like that, but it does not break the skin. So we got into experiments of that kind at the Institute of Design in Chicago, and we went in for all kinds of study of the different kinds of dirt that occurred around Chicago, and we finally arranged we took a lathe, a machine tool lathe, and organized a microscope and camera lenses, looking at your hand with a great deal of light, so your hand would not jerk and so forth. We were able to make very beautiful and large photographs of the pores, of what your skin looks like with dirt on it. And you take a picture of your hand with just the dirt at first. It looks like one thing, but it's completely different when you see it enormous and large, to be literally little hunks lodged out here on the mountaintop and so forth. And you can really see how this thing could really work. So we got into studies of all the types of dirt were known in the total Chicago area that you might get, because there are many types. You can really classify those. Incidentally, a team of the students at Institute of Design in Chicago went out and interviewed dermatologists in Chicago. First place, went to some of the local hospitals, got names of what considered the best dermatologists in Chicago, and they called on them, and every one of them said the worst thing you could have for your skin is soap. So that was worth paying some attention to, we felt, and so that if we could get a way of cleaning our skin without use of soap, it could be really very, very excellent, and we found we could. This came then to problems of different types of guns that you would use, and your supply. In cleaning those buildings, they have enormous big engines going, very big compressors and so forth. And what would be the minimum that really would work in your home, where you could take a bath for an hour out there in a room without having you don't have to have any drainage, because there's nothing to drain. How you could really give yourself a very beautiful massage, because this also massages the skin very, very well. So that we got to the point where we discovered between the Institute of Design and then later on at Yale project that did require quite a high pressure. The usual automobile filling station, where they have air compressors and tanks and so forth, go up onto about 200 pounds pressure. And this needs to be at greater than 200 pounds. It does not really work well until you get over the 200 pounds. So this isn't something you can just do with any compressor at all. You really have to do out some good apparatus, the right apparatus. We found that the Ford Motor Company had developed a special gun for the air compressor where they clean engines. A greasy, dirty engine comes in, it's clean in no time at all with a gun. And so that is the same idea, the same air compressor with a little water atomized going into it. Anyway, I now know it is highly feasible to do that, and for that reason I have not done much about that bathroom. But the bathroom that you saw, you might be interested to know, I had designed it for polyester fiberglass. The art of polyester fiberglass had not advanced to the point where it's a practical matter to manufacture more than just very single pieces. About the end of World War II in the aircraft industry, it's not yet advanced. It's not until 3 or 4 years later begin to get a polyester fiberglass of room temperature setting, where we could get into the making things such as the polyester fiberglass boats and so forth, which have all come along. So really the earliest of my polyester fiberglass realizations are in the radomes for the Air Force, and we'll come into talking about those in just a little bit here. But it's interesting that the bathroom that I designed, and really very much as I designed it, but almost all of my drawings and pattern drawings, and incidentally, most pattern drawings are not the way your working drawings are, but in the case of my bathroom, I did use the working drawings to produce the pattern drawings, and they are, if you want to look at that pattern, it's really quite an interesting one to look at. The bathroom that I did design is now being manufactured in West Germany and is getting into real mass production. The American plumbing manufacturers, so forth, have not yet started moving. They've been bothered by it, so that the Crane Company has on Fifth Avenue, on Park Avenue in New York, they have little room, but they're still taking their fixture and their own fixture, just fastening the wall, so they're not really getting into what this really means. But when you get into polyester fiberglass, absolutely continuous, that realize the cleaning capability. It's a lovely room to work in, and you find it very, very pleasant as a bathroom. But I'm quite sure we're going to be able to go much further. And I also do not want to lose those wastes and so forth, so that I think we're in for very new apparatus. It's been extremely interesting to me going to architecture school after architecture school around the world and finding students who are very enthusiastic. I've never been able to get the school to literally go into how do we develop the packaging toilet. We should be having a packaging toilet. You package our foods inbound, might as well package it coming outbound. And it's just exactly as easy. And I found that, I did develop and made a model of a toilet which had plastic sheets in 2 rolls, and the 2 sheets then become the seat, so you're sitting on absolutely clean, fresh plastic. And then the plastic goes together, and there's a heat sealer, so that then makes it and keeps making it off in bags like a sausage machine, and so there's no gases escaping. This goes off into a dry packaging, and gets your dry packages filled up, and then they're all clearly marked and so forth with the red marking what it is, and seal it up. So this very valuable chemistry can go off where they're supposed to. I also would point out to you, when nature takes a terrific amount of trouble to separate things, as for instance our liquids and the solids coming out of us, it's preposterous to put it back together again. So it's quite easy then to develop your apparatus in ways that the liquids and the solids do not get mixed up. But it's been, say, seemingly strange to me, whether it's MIT, a place where they they say we have engineering here, we have all kinds of hydraulics, we know exactly where the frictions and pipes are, and we have then big sewage disposal plants that the cities will buy, so but nobody going into direct research, see what this really means. At your own home, they're really at the site. And it's something really could be engaged in very, very, very readily, and there's no nonsense about it. But I'm quite certain then the bathroom, I've been pleased that my bathroom has gotten into mass production, but I've considered it completely obsolete in relation to what we can really do in the way of cleaning yourself and the way we ought to be really saving and packaging these very, very valuable chemistries. Now, I'd like to have my first picture tonight. I remember I said I got into grand strategy where I was only going to work on the enclosures, the environment controls, that considered the mast, became a flat mast, and got going back to my mathematics. Remember, I'd had my mathematics for a very long time. The first actual use of my tensegrity, geodesics and so forth, was in the development of the map, which I published in Life magazine in '43, where I got into the great circle grids, using the vector equilibrium as the base at that time, and later on using the icosahedron as the base. And this particular picture, just going back to those are the 25 great circles of the vector equilibrium, and those are the 25 great circles that all go through the 12 points of tangency spheres and closest packing. Those are the total number of railroad tracks in the universe that by which energy could go from here to there to go on and on in space. And this is, I was unable to find in the pictures that I saw, going back my slides, I do have a beautiful slide taken in, it was published in Science magazine, a picture of Science magazine in 1947, 48, of the first picture ever made of an atom itself, and it is just the same picture. it's really astonishing. They're the same picture, the same square. It is mildly, if you had some foreshortening and certain lenses, wide-angle lenses that make the thing you're looking at a little wider at the center. The picture, the lensing effect and their electron microscope they use was somewhat that way, so the square section is a little more open than the one I just showed you. But it tends to have a highlight, is white right in the front there. But you can make out these same 25 great circles and complete evidence. Next picture. Now here is at the Institute of Design in Chicago. I took the 31 great circle pattern, because I at first thought I would like to, because 31 great circles resolve everything goes into triangulation. And you get there are only 4 different triangles. May I go back one picture again? If you go to there's the red square, and you go from the mid-edge of the red to the center, and then go from the center out to a corner of the red square, and you see a triangle which has 1, 2, 3, 4 triangles in it. Can you make out then that in relation to the square there's a 1/8 of a square, which starts then at the mid-edge and goes to the center of the square, which is dead in the middle of the picture, and then from there to the corner of the square. So you find that there are 8 of those patterns repeated as you go around the square, and each one is broken into 4 squares, into 4 triangles. So here we have an omnitriangulation and just 4 types of triangles. And I thought that this in itself is, because everything is where in the great circles the shortest distance between points, nothing can want to be in any other, everything is just where it's most comfortable, and it's not going to transform in any other, because this is already most economical relationship. So it is inherently a very powerful structure in nature. So the picture that I had shown you of the next one with the dome, you'll see a little dome made of it, using the 31 great circles, and this was at the Institute of Design in Chicago, where I explained then that we're going to be able to enclose very large environments with very little material, and you could really then, you don't need a roof over you, and you don't need walls to keep warm. You're going to be really living in the garden instead of having a house and you have a lot that most of your garden's outside, and you can't really use a lot of it in the wintertime, so everything can be inside. And so the Students Institute of Design in Chicago went to work. We developed a 2-deck sort of veranda structure that was in the back. There's the trees and a pool out there in the front of the garden, and they did some very extraordinarily good work at the Institute of Design on this work. I got the students in Institute of Design gave them a project in which I said, I'm going to give you all the money we need, and I'm telling you that our economy is going to absolutely shut down. There's going to be no opportunity to get things anymore after 1 week. But I'm going to give you all the money you need to buy anything you need to buy in any stores in Chicago, and I want you to go shopping. And I want you to then get up your list, and I want you to price it all, and I want more than that. I want the size of the packages, things come in the containers, and all the weights. I want complete specification of what you do. There were 30 students, and they broke up into teams, and they broke up the different kinds of things your life would need. Again, coming back to the they'd work for my universal requirements list, and they would have checklists to be sure they're not leaving something out. They made really extremely good lists, and they talked them over and arguments over. Then they all went shopping around the city of Chicago in these different teams in the different areas, and they came back then with complete filling out with photographs and extremely adequately performed tasks. had that 1 week to do it, and it was just superbly done. So now we had this total shopping list and what it would really cost, and then I pointed out to them that many of the things that they had, really all of them were loose items which you could bring into a house, as you know, a house. And yet many of them are going to be associated and related. Sewing things would be near sewing things, or whatever it might be, and there would be then the things that you do in the kitchen and the cleaning of things. So there's certain things need to be in proximity one with the other. I pointed out to if you with the automobile, you have there's a dashboard, and you have a lot of things that are built into your car, and you find that they take up less room and really more convenient, and some totally, I'm not talking about what the automobile company charge you for it, I'm trying to make money, but I found to get down to the manufacturing cost. It costs very much less really have unit mountings. And so we got into the following. They developed we found out what the sum total of all the bulk of these would be, and so in the individual packages, they're going to take up much more room if they were literally fastened and arrayed in some place ready to work with one another. So what we did was to say then, well, we found that on the highway at that time there was a limit-sized truck. 8 feet wide was the limit, and still is unless you go along with special escort, and then 51, you didn't have that special escort. They didn't have the mobile home business they have today. And it could only be, so it could be 8 feet high and 8 feet wide, and it could be 40 feet long. I said, all right, we're going to have such a package. And I realized then that the package then not only then has a floor 8 feet by 20 feet, but it has actually 4 sides to the package, and the 2 ends 8 by 8. So we found that if we had hinges, this made a box, and there's hinges, so the side walls are hinged down, and the ceiling was hinged down, and the ends would hinge open. So we found that all this was perfectly practical matter. If you then designed and had things fastened onto those panels, I talked to you about jig shipping during World War II, when you began to make this delicate airplane wing in a small plant, and you wanted to be able to get it to the main assembly plant without anything hurting it. We found that we had special rigging so the things are fitted in place in the truck. So we found that we could fasten all the equipment, main equipment we had, onto these 6 panels. Four of them 20 by 8, and 2 of them 8 by 8. It's a whole lot of space. 20 by 8 is 160, isn't it? So you have 4 times 160. What's that? 62. 64. 640 plus 64 twice on the ends. You're up to pretty close to 900 square feet here. And this is many of your apartments are only 400 square feet. So 1,000 is a pretty decent little home. Really quite a comfortable home. A house is 1,400 feet. So this is a whole lot of area. And so they soon went to work on their panels and decided how they could arrange certain things which would be most logically in the center of activity. And they have things mounted on the floor base, but made fast, you see. Then there were things on the other ones that were all made fast, whether it's beds or whatever it may be, and finally the whole thing could fold up, but each being designed so that what was on this panel would fit into the space in the other panels. It was a superbly well done piece of work, and sure enough we were able to then get up this package which would contain everything that you could possibly want, and without any packaging on it, and all ready to use when you got there. So your truck box would simply open out, and there you can start living, and it can be under a dome. And we're going to be able to put up the dome in a hurry, so that there could be really very swift living. There's quite a lot about that in the Dymaxion World of Buckminster Fuller book, but we also have lots more slides, and we may have some here. I don't know if they're in the project tonight or not. But this is also then is Institute design, and there's a very beautifully done reinforced concrete geodesic dome on the 31 great circles. And there, this was done with Venetian blind stock, and Venetian blind stock, where you then made it into a you can put it on a break and make a U shape out of it. These U channels came together at hubs, and then we simply filled with this was a quick setting cement, and we put, because you had a U channel that you were filling with cement, you then had a sling across it, so you'd have cables running around. So the wires ran around this thing and filled this. I tell you, it's a fantastically strong structure. Next picture. Then we developed the foldable mobile dome out of the 31 great circles. This picture is down at Black Mountain College, and there were then only the 4 types of triangles, and there were only 4 different lengths of edges, and we had hubs. There were 4 different kinds of hub angles. So we had made little special aluminum castings where cables, the two halves were hollow, so cables could run across each other, coming in one side of the hub. There were little nodes on the hub for a tube to come on, like corks, but the cork was split open and the cable ran through inside. And these hubs then made it possible to have the cables run through between them. And you can see those hubs, they're quite prominent, of the 2 aluminum castings, and we had then continuous cable from equator to equator of the we had 31 great circle cables, flexible aircraft cable, the very finest of size. I think it was 1 2/16, so quite a delicate little thing running through these hubs. You couldn't see it, and the tubes as they came up to the hubs, we made the hubs themselves like a spherical surface, but Edam cheese cutting through the circles. So you left some, so a tube coming up to it can be perpendicular, so lets a circle onto the sphere rather comfortably. So it made a comfortable kind of universal joint. And yet there was a centering node through which the cable led in. So you have then the cable running through, and then when you tighten this at the equator, then we had turnbuckle forms with these screw jacks where you let the cable look nice and loose. The whole thing would fold up really incredibly beautifully. And then if we get the thing up, then you just tighten, everything came absolutely rigid. Couldn't have been better. Next picture, please. This is that dome at Black Mountain College, and erected outside. And then we found that when it was up, you could dimple it. They're diamonds. Every diamond, it turns out to be then two different types of diamonds. You went around pushing in the centers of diamond, the whole thing stiffened up even more. It became very, very rigid. So it had mountains and valleys, and you could put enormous weights on it. Next picture. Then we had it covered with a pneumatic skin, a double skin. And the pneumatic skin was sealed in hexagons and pentagons. Because I said you can pair triangles into diamonds, or you can collect them into hexagons and pentagons, because the whole thing goes that way. So we then made a platform. One of the ladies sitting on that platform was my wife Ann. Over in the left-hand one, you can see behind a young man in the front left foreground. There were three girls sat on the platform, and they carried this thing around. It was a strange, how extraordinarily rigid and stiff it was. A beautiful, beautiful canopy. Next picture. Then it had a hole in the top for our ventilation, so we were contemplating how the air's coming in the bottom and top, do all the kind of tricks I've given you about using aerodynamics to do that. That pneumatic skin idea, at that time, I said, the vinyls and so forth were not as good as they are today, anywhere nearly. But I told you we have one such pneumatic skin geodesic up at Bear Island, which we've gone through 4 winters and 4 hurricanes and many more hurricanes than that, and all the snow and ice, and hasn't even deflated. Just original air gas put in, nothing else. So it turns out to be a very practical idea, and it will not flutter in any wind. It's extremely, just absolutely firm, like human skin. So. Next picture. Then we had the next really large-sized dome was the Fuller Research Foundation up in Canada. It's near Montreal, and we used to, in this one, got into now the icosahedron, and we get this an 8-frequency icosahedron pattern. And I had at vertexes tubes running outwardly and cables running from the head down to the next hub. In other words, they truss the whole thing very extremely powerfully. I was trying to get down to the latest kind of structures, and I wanted to be able to do good static load testing, and these took incredible loadings. Next picture. That is that dome at Montreal in the winter of 1950. And then skinned when the spring came. And the skins are pulled outwardly. The skins are smaller than the dome itself, but pulled outwardly at vertexes, so they get hyperbolic parabola surfaces by pulling them that way, and they won't flutter in the winds either. If you put skins over the outside, they tend to wear out on a frame. But on the inside, pulled outwardly, they do not render. We've done a great many of these pulled outwardly skins. They are extremely successful. Next picture. Here then is a pulled outwardly skin. This one went to a project down in Newfoundland. Next picture. And you see those hyperbolic parabola surfaces are very, very accentuated there. This is a very light, delicate. You can count your frequency by taking the icosahedral edge and counting along 1, 2, 3. That was a 16 frequency geodesic. And I made it out of just light wires. That was the kind of wire, fetch wire. And we spot welded it, and we made it up in, I gave you the other day, diamond sections and rafts. And we made those up in the rafts, and their ends overlapped at other rafts, and they just got actually taped together. But it made extremely very, very beautiful structure. Next picture. Now this was run at MIT, the boy Zane Yost there in the background, and this one was made out of wood with wood hubs. This is one that, this type has been used a whole lot since in the dome book and so forth. Many kids find this excellent. They came up to like spools, the wood pieces then addressed to the spool. There's a top and a bottom circular plate of wood that held them into the spool, and they behaved very well. Next picture. We're still here back in around 1950-51. Next picture. And this is this is a little different now. North Carolina State College. And I had a number of very interesting projects there as the years went on. And this is what they call the automatic cotton mill. You remember that my first job that I had when I left Harvard, my first informal separation, that was up in this cotton mill in Canada. And incidentally, I'll tell you a little there that I think is important input on that job in Canada, working with those cotton millwrights from Lancashire, England, plus one from Germany, who felt rather competitive with the Lancashire men, and he was a big spinning frame man. They vied really to teach me a little better than one or the other. It was a very exciting experience. Anyway, this machinery being all from abroad, all Europe, America did not produce any cotton mill machinery. Somehow rather the people who controlled commerce over up to the time of World War I did not allow cotton mill machinery to be built in the United States. We had imported all, and primarily from England. And this is some of that machinery, and great degree of cast iron in it. Parts are very often broken, and the shipping cases coming from across the ocean, many broken parts. And the man who was the leader, the foreman of the group, would take me. This young man had been sent up there by the head office to learn about the game. He said, here are these broken parts. Will you find some place in Sherbrooke, Quebec to replace these? And I didn't know anything about metallurgy, but I began to really learn quite rapidly. And I found that there were 3 or 4 places where there were foundries in Sherbrooke, Quebec. Incidentally, the week I arrived there, it stayed 45 below zero for the whole week. It was quite, and those days there were no such thing as snow plows, and the snow just pounded up deep in the house, so that in that town, by this time, the street was going by the 2nd-story windows. And so you go out and they go up the railroad track, because it's the only way you could get to the mill, and so I found these other factories where one of the big Fairbanks Morse company and so forth. I found good foundries, other machine shops, one place or another. I got where somebody in the machine shop began to tell me what that metal was and what I needed to do. And gradually, I learned an enormous amount about metallurgy and certainly about machinery, because the workmen allowed me to stay around while they made their patterns and their castings and their forms, or if they were cutting it out of a bar stock or plate stock, or whatever what type of steel it might be, that had to be machined. I really learned all the different types of machines that you would process it to get the shape you wanted. It was a terrific kind of experience for a kid. Now, my experience then with cotton mills, it happened when I came to North Carolina State, they were eager to have the architectural department do things with other departments of North Carolina State. That's rather unusual in universities, but they did decide that they might. There are 2 very powerful departments in North Carolina State where they have world eminence. One is their textile school, manufacturing, because the cotton mills came out of north of America and were moved down into southern parts when the labor unions began to organize at the time of Sacco and Pizzetti and so forth. The labor unions in New England began to organize, and the owners simply moved right down into Carolinas, and the unions were not prepared for it, and they cut way down. In fact, the numbers of operators that I had in Canada compared to the number of operators on a machine in North Carolina, they'd been cut down 10 to 1, and gotten a lot of automation in, so that very few people were attending machines, best to the days, my early days. Anyway, they had then this, considered by far the best textile engineering school in America and possibly in the world. And so I developed then, working with the textile mills and the architecture students, we visited all the textile factories around in North Carolina, and I taught them a great deal of kids about this. So then we developed an automatic mill. Whereas the mill that I installed the machinery in Sherbrooke, Quebec, the first time was a 4-story mill. It was that because you did have water wheels, and there was at that time then the idea of having those overhead shafts at minimum length. And the mill that and we did have the same shafting and the same problems of belting down to the machines that, you see, this was well before World War I. And then when the electric motors did come in and so forth, and when the mills were transferred down into the South from New England, the cotton mill owners doing this in a very, very overnight kind of way, they put in electric motors, and they built 1-story buildings and just had concrete floors, because the machinery has to be well held. It's very heavy and a lot of vibration, so that everything is one story and individual electric motors. So I found the most modern design of the cotton mills where they were doing that still. Now all this also has to compound the fact that one of the very important conditions, the temperatures in the mills, if the temperatures are optimum temperatures for production of your fabric, the optimum conditions in relation to just the electrostatics and the lintels and things that get around, sticking on things and so forth. So they're all air conditioned. So there they are in the South, an enormous roof, and the sun beating down that roof and spending a lot of money on the air conditioning. So what I found very fascinating was to be asked to then take the architecture school and go over and see if we might do some kind of project with the textile engineering, and I undertook then to teach these kids about cotton mills, and we did visit all the factories and so forth, and then we undertook designing what I hoped would be a very highly automated, almost completely automated textile mill. And there are certain of the first machines where the unbailings and the breaking opens, and then get into the first cardings and cleanings ups and so forth, and gradually get into a beautiful twisted line, and getting into larger threads, and then into making your fabrics. And so there are looms, and there are a series of machines that things go through. At the cotton mills, they have what they call doffing. So you're winding things up in rolls. Early times, just getting sort of a blanket of the carded cotton, and then that blanket goes over to slubbers, and then blankets are pulled. Once you get the fibers getting together, you keep sort of pulling them apart, and they're brought into slubbers and sort of ropish, very soft ropes, and those gradually get at the point where you get into twistings and then get into your thread and so forth. Now, you're continually loading machines and then taking off product and moving on to the next machine. So this is doffing, and they have all kinds of wagons and containers that receive the product at the machine. When it gets full, and the attendants have to wash those, then they get those over to the next machine and loaded onto the next phase of the process to finally weaving and making a product. So what I saw was the biggest part of the labor really going on was the doffing and moving things around, and the machines were getting to the point where they were highly automated. They used to have attendants there all the time, really watching the thread would break, and all that's been well licked. Beautiful automation been done in relation to all kinds of problems. So what I developed with them was a cotton mill where you use as in building of a ship, and you go in the engine room, you see men walking on fire escape kind of operation, where you only have a supportive machine where the machine is. You don't have a lot of floor, otherwise you don't have to have a concrete floor out here for the airplane motor. We have it designed so it goes right onto the plane at the right place. You know how to carry your strength forward to that machine. So you don't have a sort of general floor. I found there's in the general factory and engineering, there's a way that you want a general floor and you can put the machinery anywhere. This makes you way overbuild your floors, because the machinery loads 200 pounds a square foot as against the live loads for human beings of 40 and 50 pounds a square foot. So what I did was to develop them the octahedron tetrene truss floors, and they're full of holes, of course. And we mounted our machinery radially rather than in parallel backs. It was very easy, really made very nice going in between them, and the product from the machines were successive. So using gravity, the product came out of this machine on this deck and came through in the machine down below. We were able to aim everything that way, so it was amazing that I was able to get a completely doffing-proof mill. And you could really have very beautiful air conditioning of the whole, because there's aeronautics of a total spherical plenary chamber. Things really behave beautifully. Air conditioning in linear rooms such as we're in is very difficult to accomplish, but in a plenary chamber you get, just remember the form of that Bikini bomb. It just became a geodesic dome. This is the form that it takes, so that you have heats rising like this goes like that, or you can involute it or evoluting. It'll always be the domical form. So it's a very natural form of plenary chamber. So we had then the machinery lined up this way, and we had the minimum surface for the most volume, so that the heat gains and losses would be very greatly improved. And finally, we had it actually coming out of the bottom, and it just really took away manufactured end products. And there was nothing wrong with that. I assure you, the best engineers in the game studied everything we had here, and there was really no fault with this at all. But it's a sad matter that the cotton mill industry is one that's really run almost entirely on statistics today, and there's no management around that looks into it is somebody really working against labor, and just they have things punching really automated, completely automated, computerized reporting, and the stockholders are living somewhere around the world, and they simply get their dividends, and there's no management that's really interested in improving the process more, that's really leaving it up to the local engineers on the local machinery. But nobody's thinking it comprehensively anymore. I found that even though I knew some of the leaders in the cotton mill world, they felt they was opening up much too much of a problem, but there was really a possibility of instituting a very improved kind of a mill. I felt as mills did go to other countries, and weaving is such an important matter that this is a form that should. You could do many things that I just did here, but there's a generalization of using gravity for the automation and using the open truss, and we had the truss really only go where machinery was and where walkways for the man, but it didn't put things where it didn't support at all. Next picture, please. And this is the truss we made at dome we made at University of Minnesota, and it was an extremely lovely dome, and we used then very fine woods, and it was very much like making snowshoes, a lovely kind of those. We used the light, delicate cross section, pretty much like the tail end of the snowshoe, and we used Dacron cables and so forth, and produced again those diamond. I gave you the diamond raft form. Next picture, please. I'd like to see more of the dome itself. There you can see one of those rafts, this big diamond raft with parallel members in it, and as a truss, and it came out very light. And we got into some beautiful production skills and setting up the jigging for it. This particular dome we then did produce at University of Minnesota. It then was on exhibition on the campus for a little while, and then I was asked to do something at Aspen, Colorado in 1951. I was asked to give the design conference major speech. So at the University of Minnesota students, we got a truck and brought these parts out there, and they put this dome up on the grounds at Aspen, of the Aspen Institute. And there were many students came in for that conference, so they went out and lived in this for a dormitory. Next picture, please. That particular delicate dome we then did move back across the country again to, we put it up at Woods Hole, Massachusetts, while I was putting up the big restaurant dome there in '53. And we used this dome for all the students. There were students from 10 universities in America who came in that project, and we manufactured in the shops at MIT, and we put the dome together, the big Woods Hole restaurant dome, down at the site, but the students lived in this particular dome as we moved it around quite a lot. Next picture, please. But it folded up, those went in parallel, got very tight. It was came on in a rather small trailer. This is at North Carolina State University, and it's another year where I worked with the agricultural engineering. Their agricultural school is also ranked very high, and we developed a growth house. Now, got into studying all the tray agriculture, the hydroponics and so forth, and we found we could develop a growth house where letting in all the sun. That was an extremely interesting course for all the students, I assure you, because the knowledge we gained, for instance, just in cell structure, we're not getting into biology, all the, I've given you the 14 facets of a tetrahedron the other day. Do you remember that? There are 6 edges, 4 faces and 4 vertexes. That's sum total 6, 4 and 4 is 14. And those could be each one of those edges could be truncated, or corners could be truncated, turned into 14 facets. And one could be truncated a little more than the other, so it would come out really quite unevenly. But the really number one world at that time, plant physiologists said, all cell structures are always in these same 14 facets. And we find that as you get into plateau and the bubble structures, all bubble structures are always 14 faceted. There can be any number of frequencies, so this can seem to be really quite a different looking phenomena, but the faces turn out to be 14. And they also do then with these, the fundamental symmetry which is there in the tetrahedron. There once was a square with a romantic flower, pure Beaux-Arts, McKim, Mead, and White. In the mood that ensued, he went factory nude, Mies, Gropey, Corbusier, and Wright. Round home to a dome, where Georgian and Gothic once stood. Now chemical bonds alone guard our blondes, and even the plumbing looks good. Let architects sing of aesthetics that bring rich clients and hordes to their knees. Just give me a home in a great circle dome where the stresses and strains are at ease. Round home to a dome on the crest of a neighboring hill where the chores are all done before they're begun and eclectic nonsense is nil. Let modern folks dream of glass boxes with steam out along Superbibia Way. Split levels, split loans, split breadwinner homes, no down money, lifetime to pay. Round home to a dome, no banker would back with a dime, no mortgage to show, no payments to go, where you dream, dwell, and spend your own time. I'm sorry about the voice, but anyway, this was a lovely dome up there, and it went on very well for quite a while. It was hygroscopic, and they got some rain, and it got a little wet around the bottom, but again, it's an interesting thing where they had some people got other dormitories excited by it and became a target for fire bombs, and it finally was destroyed. It's very interesting that nature has a way of wanting to really test things and keeps out. The number of domes I've had that have been destroyed for one reason or another is amazing. Now, this one is really not a very impressive dome to talk about. I think that I'll pass that one up. Next picture. This is a truly exciting one which occurred at the Washington University in St. Louis. Very good architecture department. You'll find that not only do we have the city diamonds that I spoke to you about in the icosahedron, but it's possible to find points which on those diamonds, and I'll just show you how you go at finding them, where we divide the total surface of the dome into two diamonds, but all the lengths of the edges of the diamonds are the same. Not a very good crayon I'm using. I think I'll use the color here. Here you have 5 triangles around each corner. And here we go to the centers of gravity of each of the triangles, and we get the diamonds. So it goes. Now, it is possible now, in relation to the 30 diamonds that you're seeing here, to find another diamond where there's a point that's equidistant from going along this line to where there's a point that's equidistant from these two points. Can you see that? So this makes an isosceles, and I can go along then each one of these where I want to get that same. Question about that now. Okay. And I'm sorry I didn't do this in yellow because that's where I got my confusion. And it keeps breaking into what are called the fat diamonds and the thin diamonds, but all the lengths of edges are exactly the same. That was interesting to find. This is the largest number of facets where I can get equal length edge. That was the problem we wanted to address at that time because we were looking for economy. So you get not only the let's see how many lines you actually have in those diamonds. You have the you got 1, 2, 3, 4, 5, 6 of these in the face. So every one of the 20 triangles has 6. So 120 of those lines here, and it gives you also. There were 30 of these. There's 60 breaking into 2 different ones. So you got 60 and 120. The 180 identical length pieces make the dome, and it was really quite a lovely dome. And then we made those. Those diamonds were made by taking boards and putting a spreader, fastening the ends together, and putting a spreader, making a little truss form. It was a very powerful, very elegant, beautiful unit. Next, may I have that picture back of the Washington Dome, and so you'll see those boards making those trusses for them, and we were not making a whole sphere, so we didn't have to make the 180. We made the number that's necessary for this particular one. So those diamonds then could be hyperbolic parabola surfaced. And this particular dome, next picture, we went on and finally made this into the, what do you call the flying seed pod, with the fat and thin domes. Here's the flying seed pod coming out. These are magnesium tubes, and made very beautiful joints for them. Next picture, please. We made pneumatic guns where we made a mast come popping up. The boys spread it out, and next picture, then they jump out of the way because this dome opens itself in 30 seconds. There were these struts coming outwardly from the vertexes are pneumatically. So we have a gas tank, and the piston just goes out like that, is released, and it takes this shape, pulls the cables, because the cables cross each other from this adjacent mass. So we saw all those things come out in parallel, a minimum form, therefore you had a dome that you really could shoot. as in a rocket and have it self-open itself. That dome is still out at. We moved it from Washington University, got down gradually to Southern Illinois University. We had it up in the yard for a yard, but they never put it into operating pop-open condition again. And I'm told recently that one of the professors has it out his house, so it still exists and could be rehabilitated. It was made out of magnesium, very, very light, extraordinarily light. Next picture. This is one at Tulane in New Orleans, where it began to get into the paperboard. And paperboard is extraordinarily attractive as a matter of economy because, I said to you, no way the man makes materials and surfaces in such velocities he does, but they're coming out of rollers as steel or paper. And being a roller, then the roller is a printing press, so you can print beautiful mathematical information and have things fold on the right lines. So this was just such a project at Tulane, but we found then we could paint the fiberglass with polyester, and it made it extraordinarily strong, incredibly strong, and good lasting. Incidentally, I've gone into a great deal of paperboard study, first at MIT, and then I went out to the Paper Institute in Wisconsin, supported by all the big paper companies, and then to the Forest Products Laboratories in Wisconsin, where we have all the art and science of making paper, and it is a I'm going to call your attention just structurally, because I've talked about tension and compression. World War I, we had only burlap bags, and burlap was used a great deal in an enormous amount of wooden crating. And there were fairly light orange fruit-type boxes of wooden crating and others, but World War II saw the paper box, and paper boxes were used all dumping goods all over the world and beaches, and they stand up great. This is craft paper, and craft paper then turned out to be, doesn't bother at all when it's wet, so that you can have cement in it and all kinds of things. It used to be in jute, suddenly we're in paper, very much more beautifully contained, not fuzzy and making powders off it. See, jute bags allow things to powder off. And so we found then craft paper has very high wet tensile strength, but very poor wet compressive strength. So if we had a container then full of cans, the cans act as a compressing unit so it doesn't collapse. All it needs is really good tension because it is already closely packed with the cans inside, so that it doesn't find any preferred shape to take. So it holds its shape. But it would be possible to get high wet compressive strength in papers as far as fundamentals of it go, but found that these are the studies we made at MIT, at the Forest Products Laboratory, and as the Wisconsin Paper Institute. And we found that if you could introduce, at the beta stage of making the paper, you could introduce the chemical ingredients that would bring about the stiffness. At the time that we were making these studies at MIT and other universities, and these were very popular at the university, I assure you, the desirability was in evidence, but the paperboard manufacturers were making so very much money, all the mills are just going full, and they didn't have any backlog time, and so nobody's willing to stop any paper mill at the beta stage to make the changes necessary to give us a high wet compressive strength. They could realize it possible, but it was a multi-million-dollar operation and tooling, and nobody going to stop down for it. So that nothing happened about that. But the point was we found it was highly feasible. But what I found it could do, incidentally, the laminates, the glues they used to use in the paperboard were really very poor about coming apart when they were wet. And they got the resource and all that got to be pretty good. They made the flutings, these flutings they brought together and double and triple and so forth, to give various degrees of stiffness. And where the little fluting just touched the flat piece of paper, then that's where you need your glues, and be sure you don't have them deteriorate. And they did then get to some that would really not come apart, and I did have one project at Cornell University where we built really incredibly beautiful paperboard hyperbolic parabola diamond dome, and got the whole, and we were assured by the paper company that we bought it from that this was resourceful and it would not come apart in the wet. But what we did then, we covered all the outside of all these pieces. They were carefully painted with polyester resin, so they're very, very stiff and strong and seemingly completely waterproof. But there were leaks in the things, and so when we got up on the roof of that same roof that you saw the miniature Earth on about 5 years later, we had this very beautiful hyperbolic parabola diamond dome assembled, and came a very great rainstorm, and she just wilted. It was not the waterproof, and they delaminated internally, which was a very shocking thing to the students. The work we put in, this over a month of work to get this lovely thing up there, and just came about a misrepresentation of the manufacturer. Those things did not often happen, we found. I'm glad to say the manufacturers were really usually very, very, very thoughtful with the style projects, but this is a sad one. The dome that you were looking at North Carolina, at Tulane then, was made using the polyester and painting, and they were very stiff. That was made for the Marine Corps, and the one you're looking at now was made for the Marine Corps, because we found then these are made out of continuous strips, which strips come together to make one of those big diamonds, because you have the parallel lines, and this comes through a roller and printed, and it prints windows into them. And it was double wall, double thickness. It was a very, very stiff dome. Next picture. That dome went up in, I'm sorry we don't have the completed dome. The Marine Corps dome did go up in a great hurry, and this is another one in, excuse me, I take back, that is a Marine Corps dome. This is at Quantico, Virginia, and very interesting things happened with that dome. The Marines liked it all right and went together readily. We had one opaque that didn't open the windows. There's windows you could fold open or not as you like. And we had it on out in the parade ground where the grass had all gone. It was just dirt. And the dome was up there, and in a few days, apparently the paperboard let sunlight through so grass would grow, but kept it from scorching. We got a most beautiful circular carpet of green grass came up. And after a while we moved it, there's this lovely circle. And the paperboard seemed to have a favorable effect that way. Next picture. This is one at University of Michigan. Next picture, again, paperboard. This is the first of the radomes, polyester fiberglass radomes, the one that I told you that the president of MIT, Jerome Wiesner, was head of the physics project for the Defense Early Warning System. And this is the dome that he purchased from me, and which he was advised by the engineers of MIT, structural engineers, would disintegrate in the 40-mile-an-hour wind. This is the one that went through there. He had it on his radar out at Lexington at the Lincoln Project, and it didn't come down in the Hurricane Cal, so they then decided to move it. This is a picture on the top of Mount Washington, where it went through 2 winters, two winds of 150 miles an hour and one of 180. And they had prepared, you see this ladder up to the top, and they had prepared a method of cleaning this dome, because they were sure it was going to pile up and get so much ice and snow on it that it would hurt the radar signals. They didn't need to. Apparently, the membrane of our triangle, the very stiff edges, they seem somehow rather like ice box making ice cubes over. It seemed to hold it, just kept breaking away all the time. They never had to use a cleaning apparatus. Next picture. This is beginning then, the big radomes getting up to the 55-footers. That first one you're looking at was only I think it was only a 20-footer. this is getting the big 55-footers. Next picture. And they went through, this is getting ready for a test of this dome at Huntington, Long Island, where the engineers of the Air Force then going to set about to find out what the strength of these domes was. They want to know. They're terribly puzzled by their strength. So they set up this dome, and when it's finished, they put ball-bearing shivs around on all the vertexes for a large zone of the top. And then they ran a continuous cable through the ball-bearing shivs down to an enormous composite pulley, go through the cable here and then through these back and forth. And all those were brought into this one great big pulley group, and there's an enormous hook on it, and it was hooked into a forged steel ring coming out of a concrete block they put in. They put hung round from all these vertexes plumb bobs. They had surveyors' transits then lined up watching each one of these plumb bobs and so forth, and watching vertexes. And they put electric strain gauges on the joints all over it. So then they got the electrical readings on the as strains that go on these gauges. They then started loading. I asked the Lincoln Project engineers in advance if they could tell me what they thought it was going to do. And they said, yes, they thought it would stand the test. They were going to load it to the equivalent of the stretch of 120-mile-an-hour wind. But they said it was going to deflect on the top like any beam. It's just going to, the whole thing is just going to bend inwardly. Well, the test went on, and I showed you my partner, and I took moving picture camera and on a roof in the building right there, so we could really look at what went on each one of the joints. What happened was it did not come evenly in the top like a beam at all. The whole dome contracted symmetrically. You could see as we got up to very high stressings, you could see rotations and so almost a ripple around of it. Vertexes each began to twist locally, very much like a jitterbug, and to contract symmetrically. Well, when they got to 120 miles an hour, the concrete block came out of the ground, and the dome hadn't gotten any trouble. So that was very annoying. So they built then a concrete block twice the size, and then this time the forged steel ring was a triangular ring coming from the block, about this thick. It parted at 150 miles an hour. So then they shifted that base and moved up to the Lincoln Project in Lexington. They then put down at strength. They finally took it up to over 200 miles an hour winds, and the apparatus again broke. They never brought that dome to destruction. Unless you brought it to a point of failure, you would not really, with electric strain gauge readings, really know how to turn this into a formula. So they never did get a structural formula, I'll show you. The only people that did get some formulas were the Japanese. This is a very lovely, beautiful dome, and all of the students, my associates who were involved in it, had a lot of pleasure with it. Next picture. That was that dome at night. Next picture. And that's one of those domes then delivered to one of their sites. You see them all around the world and this kind of a mounting. This was at Whippany, New Jersey, in the Bell Laboratories. Next picture. This is one of the domes this is one of my earliest domes being mounted on the roof of the Lincoln Laboratories, going up to be put on one of the radomes. Next picture. You saw this yesterday. This is at Thule in the northern end of Greenland. Next picture. This is then getting into the plywood domes, and the plywood are very exciting because I found it is possible to take absolutely flat sheets and that you make a sphere out of flat sheets. It doesn't sound logical, but you can. Again, remember this bending. You can take any two triangles and bend between them. I'd like you to take a postcard if you take a postcard, or you can imagine this with me, take a postcard and it's a little longer than it is now. If somebody give me a sheet of paper, just a quadrangular sheet of paper. Got a postcard? This is much better. Oh, very good. Now I can bend it like that, can't I? I'll obviously do that. That's a bend. Now I can also put a bend on that corner, making that in a triangle. I put a bend in this corner, making it in a triangle. Then I can bend this corner here, making it in a triangle. And I can go from here to here and make this into a triangle. Now I've got one of the diamonds of a geodesic feather, two triangles side by side with a common ridgepole. Otherwise, I found that a quadrangle can receive 5 bends. Out of our 6 vectors, 5 can be bent in. And this then obviously can take any 2 triangles on my dome, and this then overlaps into the next one. So if you know your mathematics carefully, then you know what the whole pattern would be to be bolted onto the next units. So that's the way. I come back then to the plywood dome. There it is. And because it gets out pretty flat, they look almost like flat pieces. I very much emphasize this. You can understand that. So that these are, you can see, this is getting into a high frequency. These are all out in Des Moines, Iowa. These pictures might body be removed there. This was an extraordinarily beautiful plywood dome. Next picture. Now those can get very high frequency and get relatively thin. And this is using the same principles, but developing a shingling orientation of the triangles. And this one's at Cornell, where I then had each one of these shingles. Inside you can look out, but there's a little air, so we call this a pine cone dome. And this on the campus at Cornell. Remove my figure in front there because I really like you getting a feeling of it. I found this a particularly nice kind of a dome. The aeronautical properties were great. The water shedding properties were excellent. Next picture. This is then getting into what is called the Pease dome, manufactured in Hamilton, Ohio. Next picture, where you got a standard pattern. Many of you are familiar with Pease domes by now. Next picture. This is a dome going into the Air Force, into a plane. This is the one going to Kabul, Afghanistan. Next picture. This dome, we were asked, Kabul, Afghanistan, 1954. If you look at your world map, then you'll find Afghanistan to the east of Iran, Iraq, north of India, and touching on Russia on its north side, and China on this way. So China, Russia, it contains the Khyber Pass. I spoke to you about there being main routes from the Orient to Europe. There was the Marco Polo one, which went by the Sea of the Baikal and Sea of Azov and the Black and so forth, and coming in through the Bosphorus into the Adriatic. But then to the south of that, coming over the desert, Sinkiang and so forth, was the one that came through Khyber Pass and through then Afghanistan. Afghanistan couldn't be a more strategic position in relation to the great pressures of Russia, China, and the enormous numbers of people in India. And in the British Empire that I spoke about, rather really the great East India Company, monopoly of the oceans, they wanted to be sure there'd never be any overland competition. And Sinkiang Pass, the Khyber Pass, is one of the real challenges to the water route. And so the English they mastered Afghanistan, kept it as a block. They blocked the overland traffic, be sure the water traffic would work. This kind of thing had become so obsolete in terms of the air age that in 1954, the British, who'd been more or less, this is one of the things they'd not pulled out of with their sovereignty, they still had an ambassador there in Afghanistan, and he's supposed to be looking out for their interests and be sure that there's no, this is an obsolete thing. No longer do you have to stop that over the possible. But the ambassador was there. It was a poor post, and he was a drunk. And it suddenly turned out in the strategic information that the Russians were very much courting Afghanistan and were about to take Afghanistan over. Afghans have an annual, every other year, the Jessin Fair, which is of very great importance. And the people come in for this fair. And it was discovered that the Russians were putting in an enormous pavilion, and the Chinese are putting a big pavilion, and all the communist countries are coming in there, and the Western world is putting in nothing. And it looked like the strategic state would no longer stay a neutral middle state, would go communist. The Americans were suddenly appraised of this, and they needed very badly to have some kind of an exhibition but there was only 1 month to go, 30 days to go. The United States got in touch with us and asked if we could produce a geodesic dome. They only wanted the geodesic dome, however, to house their show. They'd gotten up a big show. The show with the Borden talking cow and the bouncing ball bearings and the Lionel trains and so forth. It was a rather poor bunch of junk, but anyway, they needed an enclosure for it. And didn't have any time to build a building, so they asked if we could produce a dome and deliver it and erect it in Afghanistan in 30 days. We did produce it, and we produced it, and I made the State Department, the government officers come down. We erected it at the airport at Raleigh to be sure they wouldn't say after we got there that they didn't know how to put it up and wouldn't pay us. So I found you have to be pretty tough with that government now. And so did work, and so we erected it, and the picture you saw, they were putting into the airplane. It had to go in one DC-3, the DC-4. It had to have one of our engineers go with it. That's all. And so it did get to Afghanistan. It did go up in 48 hours, going up in 24, except that there was a holiday.